testers, and developers. Prior to that, Rob was principal engineer at Magma Design Automation and originally a senior design engineer at IBM involved in numerous technical areas for development of IBM Power and S390 systems. Rob has in-depth experience in software development, electronic design automation, IT management, semiconductor technology, microprocessor circuit design, and chip construction methodology. In his career, he had the privilege of working in multi-company collaborations, understanding the dynamics of multiple players and working towards win-win solutions for all players. He is the holder of 13 US patents. As General Manager of CHIPS Alliance, a part of the Linux Foundation, Rob is working to build the open source hardware ecosystem to create a collaborative and worry-free environment for participants to work in and build innovative products of, of open source component. So this is all about Mr. Little bit introduction about Mr. Rob Means. So we welcome you, sir, on behalf of AICT Academy Jaipur and other partnering academies, sir. I hope the participants will really get benefited out of your very vast experience or 40 years of experience you have. Thank you, sir. It's over to you, sir. We are going to make you presenter. You are presenter now, sir. Thank you, sir.
Yeah, Mentor, can you record, please?
Yes, sir.
Okay.
Yeah.
And Rob, thanks for agreeing and presenting here. Thank you very much. This is Ganeshan from IBM OpenPower. Thank you.
Yes, Ganeshan. Yes, it's a pleasure to hear your voice again.
Sure.
So let me go ahead and just bear with me for a second here while I. All right, I guess we'll just do it this way. Let me put in a slideshow. Are you seeing this slide now? Accelerate
Yes,
time
sir.
to market?
It's visible, sir. It's visible.
Oh, very good. Okay, very good. There's always some technical challenges in these things, so I'm glad this is working so far. So anyway, thank you everyone for the kind introduction and welcome. It's my pleasure to be able to present here today. I still consider myself part of the IBM family, although I obviously have had other experiences in my career. I really won't go into an introduction. I will just say that I did do extensive work on Power 1 through Power 4 at IBM in Austin, Texas, and it was a great experience in my career, and I learned a lot about many different topics, and it has served me well and continues to do so to this day. I guess the one thing that I will say here, just as part of the introduction, that I've been in the industry for a long time, as was mentioned earlier, and suffice to say, change is the name of the game. It's just change is happening all the time. Every day you pick up your tablet or whatever and you read something, and it's just amazing the progress that's continuing to go on in the technical community, and it really makes it exciting. It keeps me motivated to continue to work because I do like to learn things, and I enjoy interacting with people from all over the world. So again, it's my pleasure to be here this evening. So let's talk a little bit about background. So I talk about accelerating with more than more, and I think for most, at least for most of my career, we've always relied upon silicon scaling, right? It originally was bipolar, then we went to CMOS process technology, and the amount of transistors that we could pack onto a single die with improved circuit performance and better power, getting more transistors in a given area, just continued to increase. So it's really been a tremendous run. Unfortunately, it's getting a lot harder to accomplish that with process technologies, and the amount of non-refundable engineering investment, or NRE, that is required to advance from process node to process node has just gone up tremendously. So that makes it a lot harder. Another technique that has been used, and this goes back to actually IBM mainframes and also on Power 1 and Power 2, and I don't think Power 3 if I remember right, but anyway, was the usage of MCM technology, right, where you basically had, if I recall correctly, on Power 1, it was 6 chips that were together. And of course, that eventually went down to one single chip as you started to see after Power 3 and going on into Power 4, as an example, and on into today. Another advent that has occurred, though, of recent years, which was brought forth by AMD and Intel, is AIB, which is basically chiplet technology, which allows for smaller die to be used, but they're put on a larger package, and it has a defined interface protocol, both electrical and signal-wise, that would allow you to put different pieces together very easily. Another advent that's occurred to help relative to alleviate the challenge with process scaling and to improve performance is the notion of accelerators, right? So custom accelerators have been created, right? It could be something like Oracle created, which I was part of on the M7 chip, which was the database acceleration unit, which is where instruction traces from actual database calls were captured, and then it was determined in hardware how to help accelerate that. So a special acceleration unit was built and put in the M7 microprocessor, or Spark microprocessor. We've also had a lot of work in terms of graphical processing units, special accelerators for artificial intelligence, and of course we're seeing the notion of embedded FPGAs inside of chips as well. A company known as Achronix, for example, is doing that type of work of having an FPGA inside of a chip that could then be configured based upon the actual workload. And finally, let's not forget the acceleration or performance that's capable by having better and better compilers and also software libraries, right? Those are very important aspects that perhaps are not always thought of by different folks, but nevertheless is an important part of the overall performance story. So as you can see, there's many different areas or opportunities for improving performance just on traditional scaling. But there's something different here and something new, and that's more what I want to talk about today. And that's really what I call industrial evolution, which is moving from siloed to a collaborative type environment. If we look back in time, this was certainly true at IBM, but it was also true of many large companies. General Electric as being one of them, Ford Motor Company is another, right? Where everything was done in-house. So for example, I know like Ford had its own rubber plantation. They had their own foundry to actually pour the cast for engines as an example. Everything was done at that location. That was true for General Electric as well. And IBM, of course, years back had its own foundry as well and built its chips, did its own packaging, did its own EDA, the whole thing from soup to nuts, literally. But now we've moved on where that's really not necessarily a cost-effective model, right? It's a very expensive type of R&D investment. It's hard to get talent in all those different areas and to manage that entire supply chain, if you will. So now we're going to go to what I call more of just-in-time type of delivery, where you have different suppliers provide you things or ingredients necessary to build your product, right? That, again, that could be EDA that's provided some of the major companies, could be by a foundry partner such as TSMC, Global Foundries, or Samsung, et cetera, right? So it's really about managing all those pieces together, and your company perhaps just focuses on the actual design in and of itself. But now we're really going into what I call more of an open collaboration, right? That it's just too hard to necessarily have all the expertise present in your company to do work on a particular topic. So by collaborating with other companies in a non-competitive environment, if you will, to reach a common goal, that really is going to help accelerate or modulate the R&D spend and the NRE that is needed, but yet allow you to gain time to market. So this is really kind of a change in thought process, particularly in the hardware arena. The software guys learned this quite some time back. So really, if you think about the evolution of software, you may recall, right, that way back when it was punch cards, it was assembler. I started doing programming in Octal, believe it or not, on a Hewlett-Packard rack-based system. Flowcharts, line printers, terminals, a whole different types of editors. And some of these you will still see in existence, like ISPF. You'll see that if you go to a Costco and look at their terminal that they have for returning items, right? That's actually an IBM editor, right? So DBX, GDB example, right, are other examples of debuggers that were commonly used and still used by many. I still use those debuggers. But now we're really talking about more of an object-oriented type design. There's a lot of productivity tools. You can write software one time and run it anywhere, as the case with Java and other types of languages such as that. Reusable components. There's just tons of libraries. And quite honestly, it's a lot more fun, right? It's not this hardcore stuff that software developers had to endure years ago. And what this really boils down to is accelerating innovation, increasing productivity with less resource. And of course, in the early 1990s, there were many different types of OSs, right? There was HP Unix, there was VAX VMS, there was Solaris from Sun Microsystems. Windows, of course, which is still around with us. IBM had OS/2. And out of all of that, though, a person, of course, as everyone knows, Linus Torvalds, started writing a version of Unix for the x86 platform known as Linux. And at the time when this first came out, it was very doubtful that this would have any degree of success. But of course, as we know, as it turned out, that really caught on by wildfire, spawned many different businesses and ways of this is being supported in the industry, and really has become a commercial standard, at least in the engineering world, certainly. So the Linux Foundation was founded based upon the operating system. Of course, it's much more than just that right now, right? CHIPS Alliance itself is part of the Linux Foundation, as is OpenPower too, and the RISC-V Foundation too, right? But it's got over 1,500 members in 40 countries, tons of developers and many different projects, right? So a lot of IP that's being created in a collaborative open source foundation. So I just listed a bunch of them here, but you get the idea. So the real question here is, well, what about hardware? Where's hardware going? Well, of course, hardware or computers, so to speak, are ever present in our lives every day, right? So anyway, from healthcare, advanced computing, as I already talked a little about on the other chart, to 5G communication, is present everywhere. And as you can see, the number of devices that are present in our daily lives just continues to increase. And a statistic I heard recently, just not too long ago, was that a given modern vehicle has over 300 chips in it right now. So you can appreciate why, when there's been challenges with semiconductor supply chain, it has a definitive impact on the automobiles being manufactured. So if we talk about open hardware growth, CHIPS Alliance RISC-V, right? So open source hardware has been a real success, predicting for RISC-V, right? They are up to they're predicting now 80 billion cores by 2025. Intel, of course, made a recent investment of about $1 billion into that. Now, CHIPS itself is 4 years old. We've got 40 members right now, or 41 really, I should say, and it continues to have active participation and growth, both from companies and academic researchers as well. So what is CHIPS Alliance about? Well, really what we are championing is an overall open design ecosystem, all the way from specification, RTL, open source PDKs, EDA tooling, physical implementations, standards, right? And as I mentioned earlier, there's many different participants. So this is what we're trying to build, is an open platform that allows for innovation across the board by collaborating companies, universities, and individuals. And we do this by having a number of different work groups that exist. I'll talk a little bit about some of these, what their activities are. We are just now in the process of creating a new work group. So there's no limit on work groups that we do create. We create these based upon the actual need of the industry, but we're going to be creating one now on Root of Trust with some new companies collaborating in CHIPS Alliance on this. So I think that'll be an exciting detail that hopefully I'll be able to share more on going forward. But anyway, just to give you an idea of some of the different areas that we do look at. So a key part of all of this, of course, is the notion of having an open source PDK. And this was originally championed by Skywater Technologies and Google, but now Global Foundries has also brought forth an open source PDK at the 180 nanometer node. And so that's really a significant thing. And you might say, well, what's the big deal about that? Well, for those who haven't had the, I shall say, unpleasant experience of having to work in this area, I did that in large part in my job at Oracle, which was with TSMC, but you would spend a lot of time negotiating multi-way NDAs, or non-disclosure agreements, between the foundry, between your different EDA partners, and they all had to be signed with the respective legal teams. It would take a long time. Well, what these companies here have done is they basically have taken that off the table, and this allows for collaboration across the board. So it's very much attuned to what is trying to be done in the open source community, and to enable different groups to collaborate without the worries of the overarching legal complexities associated with that. Now, of course, the question will come up was, what about sensitive IP? So that's an area that we are looking to address, and OpenPower actually has come up with a good way of doing that. And what I call this is basically like a secure garage, where participants are able to enter into the secure garage by signing the necessary agreements to enter the garage, and keep as part of that the proprietary information necessary. So that's typically the case for more modern process technology nodes. We need the type to do that thing. So that's something that we are looking at doing, establishing in chips as well. Again, OpenPower actually established this as part of their efforts in some of the work that they are doing. So that's a good model. And of course, something like an obfuscated API may be something that could be beneficial relative to some of the EDA software as well to help obscure some of this information. So if we think about chip design hierarchy and where we're trying to go, I think about it this way, that really it's architecturally the same. You have a given design hierarchy, but collaboratively it's different. So on the left, if you think about it years back or even yesterday, you could say that everything was developed in-house, right? That, you know, you could have a colleague, you all wore the same badge, if you will, and they were responsible for different parts of the chip design. Whereas in more recent years, you have relied upon IP to be purchased from a supplier. This could be an IP vendor such as a Cadence or a Synopsys or other library provider that would provide you something like maybe like a SerDes, right, or a PCIe, right? You could go buy that physical macro or logical macro, as the case may be, and use it as part of your chip. And what we're trying to do going forward is in the open source community is that it's going to be a mixture of purchased, in-house, and open source. And that's very much like what the way things are in the software world are, right? That some of the software is written internally, some of it you may purchase the library, and some of it may be open source, right? So it's kind of a creation or a mixture of different pieces. And so this really comes down to enabling design reuse and interchange, right? So it could be soft IP, in other words, just like an RTL macro that you buy, and then you synthesize it to your target technology. It could be hard IP that's already instantiated in your target technology, or you could be doing something in the chiplet space where you're picking up different elements from a menu of a supplier to build the IP that you're interested in and packaging it in a chiplet type thing. So let me talk a little bit about some examples from CHIPS Alliance. So again, as AIB, as I mentioned, effectively, it's a protocol that exists between these different chips, and it defines the signal and electrical protocols to be able to transmit and receive information between these. And effectively, the technology that has been provided through AIB is that it's technology and foundry agnostic. There's a number of different things that you can pick from an existing menu to build IP that you want, and then also add into that chip design that you yourself want to incorporate into the overall package technology, provided, of course, that your design in and of itself has the follower leader protocol that's defined by the AIB protocol. And of course, this is now being more widely adopted by industry in the UCIe interface specification that Intel is going to be participating in as well. Another part of what CHIPS has in its portfolio is a RISC-V core, the Swerve core that was donated by Western Digital. It's both the EL2 and EH2 type of cores. That includes the RTL and also the verification bench that goes with that, as exhibited on the right. And that verification bench, of course, can be used in Verilator, which is an open source functional simulator, or it could be something from your favorite commercial supplier, such as VCS from Synopsys. But the point is that you can pick this up and use this to design higher level functionality. And in fact, we actually have a project that's coming on board in CHIPS right now that will be using this in this exact ecosystem to help build higher level functionality. So that'll be interesting to see how that progresses. One project that we are trying to get going is a collaborative open source memory controller. You know, the idea is to be able to explore and look at some of the different use cases that exist with this for security on edge computing for the data center, and also for mitigating row hammer attacks. We could use a power core on it or a RISC-V core to be able to do that, depending upon which company ends up wanting to participate and who ends up using this. But what we'd like to try to do is to take this out sometime in 2023 using an advanced process technology node. And that, again, would use the collaborative garage model that I described in the earlier chart. But this is something that we're trying to get going, so stay tuned for that. Talk a bit more about EDA. We have a lot of activity in this. So I think a key question behind all of this is how do we get more people to participate in hardware? As I've talked to different universities around the world, it continues to be a challenge to get individuals interested in hardware engineering. And if you compare that for hardware versus software, I kind of say it's like mixing oil and vinegar, right? It's really two different cultures, right? And in some ways, hardware is kind of like a black magic or a rocket scientist, as you can see here on the left, right? Whereas software, you know, it's much more approachable, right? It's kind of fun. It's like if something doesn't work, you just change it and you know you fix it and away you go, right? And so, one idea that's being bounced around you know, in the state of New York, for example, is to have certificate programs to get people comfortable with hardware design, but not necessarily requiring a four-year engineering degree or beyond. So we'll see how that progresses. But really, what this is all about in the end is hiding complexity, increasing productivity. When I worked on Power 4, then also at Sun Microsystems, it was entirely a transistor-based design. So literally it was hand-tuned, placed, and routed. So you can imagine for a large microprocessor, that's a very complex problem, and also an inhibitor of productivity. Now, granted, tools were developed to aid in tuning, to aid in performance analysis at the transistor level, but that's non-trivial as well. So what came to be realized pretty quickly as we migrated to later processor development activity and also later process technologies, that we really needed to stay to a gate level type representation and use tools to help place and route and time the design at a gate level as opposed to at the transistor level. And that's really the first level of abstraction. But really to help move that further forward is, of course, we described our designs in RTL, which is really in some ways, if you think about it, it's like a hardware assembly. That could be Verilog or VHDL. And what we're seeing now in industry is we're taking more of a software approach. We're using object-oriented languages such as Scala, we're using Python, System C, System Verilog, really to help abstract the level even further and to make designers more productive and to enable easier design reuse and also to integrate verification of part of that. So we're really going basically similar to like what happened in the software world of doing code in assembler, if you can believe it or not, to more intermediate languages or structured languages. We're now going more to object-based type of things. And of course, at the end, we do a compilation and that gets us down into the layout, or as in the case of programming, into machine code, right? So it's really one and the same. It's all about, again, accelerating innovation and increasing productivity with less resource. But there's another aspect here too, which I want to bring up, and probably most on this call may be familiar with it, but I think it's important, is that, you know, very much earlier thinking on chip design was kind of like launching a mission to Mars, right? It's like all systems go. You know, we've gone through the entire tape out checklist. Everything is done. We're going to push the button. We're going to send it off to manufacturing, right? And so it was kind of this natural paranoia, right? Fear of failure that existed in the engineering community, right? And that certainly is still true, really, for modern processes for manufacturing chip, which is a multi-year oftentimes development effort requiring millions of dollars. So we're really trying to work to simplify that, right? We're trying to remove this failure is not an option type of paradigm, right? And to allow for many tape outs at low cost older nodes. And you can think of that as, you know, kind of like training wheels, if you will. And don't take that the wrong way, but it gives you an opportunity to try out different ideas, to learn, and that if something doesn't work, that's okay, because it's not a huge investment as would occur on a more modern process node. You can think of it like driving a high performance race car, right? Or maybe you know you're if you have kids and you have a teenager and it's like putting them in a high performance sports car to learn how to drive. It's like you probably don't want to do that. You probably want to put them in something that if it gets dented or wrecked, it's like, oh, it's okay, right? So that's kind of the same type of idea here too, right? That's what we're trying to help move forward on. So we have a lot of effort in chips relative to different design languages. I mentioned and chisel, right? And the overall idea, again, is to help expedite designer productivity and to have libraries of functionality so that we can build things and encourage object-oriented thinking, right? And That also then helps participation by a broader community. You don't have to design or understand down to the transistor level to be able to design and build a chip, right? And we have high-level synthesis to help generate RTL, right? And then implementation tools to realize and provide guardrails to let you know when something is not right. And so one of the things that we have done in chips through collaboration through a number of companies basically is to create a design language framework that allows us to bring in System C, System Verilog, and others into a common set of parsers that then go into a universal hardware data model that applications can be built upon, such as the open source synthesis and Yosis, or the open source simulator Verilator, which also then of course takes in the unified hardware data model as a result as well. A key aspect of what we do also work on or with is with Verilator. We've been continuing to, which is an open source functional simulator. We've been continuing to work on that and extending it to have a stratified scheduler, method randomization, and class support, right? So this will help us better handle System Verilog as one example with UVM to help move that forward, right? So Ant Micro has made a lot of good progress on that in conjunction with Google to help move this thing forward and continue to improve progress on it, or performance on it, I should say. A key part of the overall implementation is automated ASIC flows. So as many of you know, there's been a substantial effort at the University of California, San Diego, and Precision Innovation, which is a company formed around this to help build an open source digital design construction application set and then flow known as OpenLane. So there's OpenRoad, which is the actual implementation tools, which has the steps listed on the right, and then OpenLane, which is the scripting language that's on top of it to be able to construct a flow to do different blocks. So these contain the different key pieces of this, and this has been used on some more modern process technology nodes such as Intel 16 or on Global Foundries as well. Another activity in CHIPS Alliance is the Analog Workgroup, which is all about automating analog. And we have participation by a number of universities, including Michigan, Minnesota, as part of that, and UC San Diego as well. So we are using a line from Minnesota to help construct the bit cells, and then we're using OpenFASIC to help pull together the different bit cells that we do create. And this kind of shows the different types of operations that FASIC can have in and of itself. You'll see on the far left the traditional analog type of flow, and that's very much, as I was said earlier in the talk, that's how Power 4, as an example, was designed using pretty much all schematic entry and going through those steps. And what we've seen, of course, Sun Microsystems tried to do the same type of thing, but what we've seen because of the problems relative to productivity, both in analog and digital design, that having a more structured-based approach, cell-based approach for both analog and digital makes a huge difference in productivity, time to market, less designers required. So that's a huge improvement. So as an example, we've created a PowerMux unit, a PMU, with different aspects to it, and the individual bit cells were created by a line. And this gives you a different idea of some of the different pieces that are done in this. And then OpenRoad was used for the place and route of this. And this has allowed us really to do an order of 1,000 of different design variants by using these automated type of techniques. So it really is a huge improvement in the overall designer productivity. Another workgroup they have, which we recently formed, is the FPGA workgroup. And this was built upon work known as SymbiFlow originally, but the idea is to have a fully open source flow for FPGAs. We want to drive open source tooling, IP, and research efforts in this arena, right? So the idea is to be able to bring together academia, industry, and FPGA vendors. So we're focusing on open source tool chain and interchange format to help pull these different pieces together. And we will eventually go farther to be able to actually build a open source place and route environment using these tools, the FPGA interchange format being the first step to allow different contributors to participate to work in this arena. So a key aspect of all of this, and you can say, well, this is all great, right? But it's building trust, right? It's more than just having an open source IP and application catalog, right? You have to have confidence to know that, you know, what you're doing or what you're using is going to give you the right answer and it works, right? Software has built this up over the years through a community and has established this with confidence and discipline, right? Of course, there's a difference with hardware, right? Because something that may work at 20 nanometers may not work at 7, right? So there's different electrical effects that you have to consider and deal with as you change process nodes. Now, of course, the Apache 2.0 license, which is what we champion relative to our group, is it provides a barrier-free entry to allow you to pick up IP, whether it be hardware IP or EDA IP, and reuse it as you see fit for doing your activity, right? And of course, hardware IP, you know, we need reference flows to build in your process target technology. We need to build tape-out productization confidence, and we need a prevalence and availability of cheap shuttles to help have as a proving ground. And of course, EDA applications in and of themselves is a somewhat different story. So let me talk a little bit about that. So some challenges with open source EDA software really are as follows, right? Technology access, right? It's more than just comparing numbers between two applications, right? You really need fundamental information. Typically, it requires an NDA, but fundamental process technology information to be able to properly construct and verify the EDA application that you are interested in working on, right? And I came up with this term because I heard a presentation just the other day about an open source analysis engine, and I called it parameter roulette because basically the developer could not really find anyone who would tell them what a particular parameter meant. They were effectively guessing what it might mean. So, you know, you shouldn't need like what I call a Rosetta Stone to translate from the hieroglyphics of what the process technology parameters are into something that an application can use, right? That just isn't going to work. That's not a recipe for success. So we need to get that fixed, right? The other thing is that EDA developers don't grow on trees, right? It's kind of a unique mixture of hardware and software skills, right? So that's the exact background that I have, and you know that's how I worked in IBM EDA for quite some time, and then beyond that, also at Synopsys and Magma, right? So it's a detailed knowledge of highly special areas that's often required to do this type of work. Another key aspect is testing, qualification, and quality of results, right? So those are both key parts of the overall development process, right? You need to know when you've broken something, when you make a change to your code, whether it be an enhancement or a bug fix. But the point is that if you're going off course, you need to know that, right? Now, another key aspect is qualification of foundry data. That has to be, in other words, does it correlate extraction and timing, right? And I'm talking field level, field solver and spice level type of qualification, which means that you have test circuits, metal stacks, etc., that you can correlate to and really get down into the details to understand what's going on. And finally, then, does it adhere to design rules? Is the DRC correct? That's another key aspect. And methodology and support, of course, you know, for any of these things, you know, trouble always does arise. It happens at the worst time. So you need somebody you can call who can help you with this, right, in terms of how the application works, how it applies to your design, to diagnose problems or resolve issues. So this could either be a resource that you and your company has that you've assigned to work on these problems or to help, you know, do development work, or it could be a services company that's been built up around to provide these types of things for you. So if we put it all together, this is kind of the big picture, right? But it just shows you all the different aspects of design, some of the tools on the right, the library, physical or logical macros, a verification test bench, etc. But basically an open source verified and trusted IP library. And so the question I ask you is, how far along are we on this journey? And are we there yet? Well, the short answer is no, we're not there yet, right? And we still have quite a bit of work to go. But I think we are making good progress. There's a lot of interest in the community, a lot of excitement about this. So I think we're definitely off of the starting block, so to speak, and down the track. So really, open source model is really IP and your innovation to make your product, right? So it's an open IP catalog. It's your ideas and innovation that then yield your product. right? So that's really what this is about in terms of putting together these different ingredients. That's what CHIPS Alliance is championing and helping to bring forward to the hardware world. And really, it's building an open IP community and business services, right? We have a developer community, service companies, as I mentioned, who you can call if there's trouble, right? And then an open source repository that can be maintained by the community, right? To provide quality release and application engineering. So in summary, CHIPS Alliance, it's an open source hardware verification tooling are here. They're gaining momentum. There still is work to be done for sure. Hardware engineering is learning a lot from software, talking about abstraction, object-oriented design, libraries of functionality. Companies and universities are collaborating on mutual challenges of interest. We're making progress in this area. It's great to see companies really starting to get involved in open source and to pick up some of the great ideas that are coming out of our universities. Business models are evolving to embrace open source development. We're not totally there yet, but certainly there's a lot of progress that is being made in terms of change of thinking and also realization of the opportunity value that's here. And companies are innovating at higher levels. They're leveraging open source IP and helping to accelerate the time to market. And CHIPS Alliance, as part of the Linux Foundation, really provides a collaborative venue for all to participate. So I encourage you to check us out, and there's the pointer if you're interested in joining us. So with that, I will end the talk and turn over for questions.
Rob, thank you. Thank you for the wonderful presentation. And also, please do share in the chat window any links, where students and faculties and researchers can get the details of, the CHIP Alliance and the groups which you mentioned.
Oh,
So
sure.
that people can join,
Thank you, sir. Thank you for a nice presentation, and I hope the participants have enlightened with your rich experience. So there is a question, sir, from the participants. What is the procedure to test the chip? Can you please answer the query, sir?
Yeah, I'm sorry. Can you repeat the question for me?
Procedure to test the chip.
Oh,
What is the process?
the question is there a process or a procedure to test the chip?
I didn't really talk. Yeah, you mean about silicon verification you're referring to?
Yes, that's correct. That's
Yeah,
correct.
I did not really talk about that, and CHIPS Alliance itself has not delved into that arena. I certainly am aware of the processes necessary or steps necessary for silicon qualification. I'm also familiar with design for test as well, but we really have not looked into that.
Any more questions, participants? Do you have more questions? So I don't think that there are more questions. Thank you, sir. Thank you for your time and accepting the invitation for be an expert speaker in our program, sir. Thank you, sir.
Yeah, Menka, I have a few things, to discuss with Bob. Okay, Rob, so what is that you are expecting from a students community from India for Chip Alliance? What are all the things you are expecting so that the OpenPower Academia has got the India-wide reach? We can help you out also to develop that ecosystem.
Yeah, I think getting participation by students in India and universities would be wonderful. I think it's an opportunity to aside from learning chip design, it's also an opportunity to start to gain an understanding of EDA algorithms and starting to do development work on some of the open source EDA applications.
Yeah, that's good. And also, like, in India, there are nearly hundreds of startups, who are investing right now in semiconductor industry. So there were some startups, in previous days calls, and they joined too, but today the people could not join. But what is that input you have for them actually? What are all the things they can get benefited? The startups.
Well, I think Well, I think startups certainly can benefit from participating perhaps in one of our work groups, but also in terms of looking at some of the IP that we already have and using that to build product, or perhaps contributing back into the chips repository as they build different things and parts that they could potentially open source that would be beneficial to others in the open source hardware community.
Okay, that's good. Definitely, because I'm going to have another conference with the startups too here.
Okay.
Bunch of startups where we will communicate about this chip alliance, for a few minutes and
Okay.
see any tractions, we can get out of that. Sure. Thank you. Thank you, Rob, for the presentation, and really appreciate it with your time
Sure.
and effort and dedication. I know it's the time is too late there, but thank you very much.
Oh, you're welcome. Thank you very much for the invitation. I appreciate it.
Yeah, thank you.
Yep. Bye-bye.
Thank you, sir. Yeah, so let's welcome to our next speaker. Am I audible to everyone?
Yes, Menka. Yeah, we can now welcome the Google, the expert, Johan, and and we can start the
Yeah,
Google
so our
session.
next speaker of the day is Mr. John Euphrosyne. He's from Google. So Mr. John is developer and program engineer at Google, and he's working with OpenSilicon. So now he's going to speak for next 1 hour. So welcome, sir. Mr. John, are you there? Hello? Mr. John?
Yeah, hold on.
There,
Yeah,
but
Jogan, your
yeah,
session started little early, so please, accept accept it, and probably you can say a few words, and then we can play the
yeah,
Tim answers video.
yeah, I
So
was able
Mr.
to join
John
there.
is going to speak on OpenLane flaw of GDS2 generation with Google Cloud. So yeah, he's going to speak. Thank you, sir. So I'm going to play your video.
Hello, can
Jogan,
you hear?
you want to address the audience a little bit for 1 minute, and then we can play the video.
Yeah, can you hear me okay?
Yeah,
Okay.
perfect.
Yeah, so I'm sorry I wasn't able to present. Like I have some technical issue that where I can't seem to be able to present my screen. So I hope you're able to play the video. The video is actually from back in May, where someone else from Google called Tim Ansel, who actually started this whole open source silicon program at Google that we are sponsoring, gave to the RISC-V conference that we had here in Japan. And so it's I think it's relevant also to the OpenPower ecosystem, because like OpenPower is another like big open source ISA, and we've seen like also like submission to the Google sponsor shuttle program that we are using the OpenPower architecture. And I think that's one of the biggest design that we've seen is called microwatt, and that one of the most complicated design and more complex design that got submitted to the Google sponsor shuttle. And so I hope you will be able to find information in that talk, and I'll be available after the talk if you have any question about the program. Can you hear me okay?
Yeah, yeah, very good. Volume,
Yes.
please.
So if you can go with playing the video, I think that's okay.
Yeah, volume, please, Menka. Volume. Menka is not audible. Can you increase the volume as per the day before session, which we had? Menka still is not audible. Is there a way you can increase the volume, please?
Sir, actually, there is some issue, and the volume is full, but this is not able to take the system audio to the Cisco WebEx, sir. So this is the issue. I'm trying to sort it out, sir.
Okay, take your time. Actually, we
Okay,
have
sir.
anyway for the next session. We have few minutes actually. So yeah, sure. Just try to get it fixed.
Yes, sir. I'm trying, sir. मैंने अनम्यूट किया, अभी मैं प्ले कर रही हूँ। सुनाई दे रहा है?
Yes, ma'am.
सुनाई दे रहा है क्या?
Okay, okay. Ma'am, is it audible?
No, not yet. Not yet.
No, it's not audible.
1 minute.
Just play once again so that I can just check. It's a stop right now.
Yeah.
Not audible.